Can you solve the question 5a minus ab is equal to 9b squared, where a and b are positive integers? This is a tricky question. It was used at intermediate maths Olympiad level to test 13 to 16-year-old students. And the thing that makes it quite tricky is that we might find a solution that works. So that may lead some students to believe that they have solved it. But because there's a and a b and we only have one equation, so we have two unknowns and one equation, there may be multiple solutions that actually work. And to have a valid Olympiad proof, we're going to need to find all of them and prove, not just find all of them, but prove that we have found all of them. So the only way we can actually do that is, rather than just trying to find and call guess values that work, is we're going to have to use a logical, rigorous method. We're going to have to learn some things about this equation in order to do that. So what can we notice here? You've got 9b squared. Well, b squared is positive, so that means this is a square. So you've got 3b all squared, okay? And on the left-hand side, we can factor out an a and get 5 minus b. So a times 5 minus b is a square. Now, we're also told that a and b are both positive integers, so they are whole numbers. So that means that b, and since this side has to be positive, both of these factors are going to have to be positive as well. We know that a is positive. 5 minus b is going to have to be positive for the overall thing to be positive. So 5 minus b has to be greater than 0. So that means that b has to be less than 5. So we have 4 possible cases here. b equals 1, b equals 2, b equals 3, and b equals 4. And we can actually just test each of those in turn. And this casework of just testing each case, seeing if there is a valid solution, is such a common technique in Olympiads, because it just is. Whenever we've limited our options down, we often get to this point where there's just a few cases that we need to check. We do need to check all of them to make sure that we have a valid mathematical proof. So in the case when b equals 1, we get 4 times a. We know that this side is going to have to be a multiple of 3, and it has to be a square. In the case when b equals 1, actually scratch that last bit. In the case when b equals 1, our right-hand side is just going to equal 9. 4 times anything will never equal 9, so that's not going to work. When b equals 2, our right-hand side is going to equal to 6, and then this 5 minus 2 is going to equal 3. 36 divided by 3 is equal to 12. So b equals 2, a equals 12 is a solution that does work, okay? Just because we found one solution, though, does not mean that it can't be more. b equals 3, 9 squared is 81. So 2 times anything, 81, if a is a positive integer, so that does not work. And then b equals 4, 12 squared is 144. Well, that works if 5 minus 4 is 1, and a is just 144 as well. Here, again, a and b are both positive integers, so that works too. So there, we've checked all 4 possible cases. 2 of them didn't work, 2 of them did. We found 2 pairs of possible solutions, and we have mathematically explained why we have considered all the possibilities, and this is a rigorous proof. We've explained why it's a rigorous proof, and I've talked through it. Of course, you need to add some more mathematics here to actually have a valid Olympiad mathematics proof as well. If you liked this and you want to remember that you always need to check the cases and learn about the equation before you actually dive in to try and start considering the cases, because that useful information was figuring out that b has to be less than 5. If we hadn't worked that out first, then this all would have been very complicated. So you want to remember to look for things like this before you dive into your casework. And save this video, and if you liked it, share it with a friend.